My name is Greg Miller, and I'd like to thank you for showing up to this early 9 a.m. talk about time programming fundamentals. Happily, this doesn't feel very early for me since I'm from the East Coast where it's already about lunchtime. However, despite that time difference, if an East Coaster were watching this talk right now, we would still agree that the talk is happening now. And these are the aspects of time and time programming that I'm going to be talking about today. You might call it human scale time. Very briefly, I'm not going to be talking about clocks or timekeeping or time synchronization. And since there's always some comedian in the room, we're not going to be talking about space-time or relativistic effects either. I've worked at Google for about 10 years, and I've watched Google's C++ code base grow to well over 100 million lines of code. Some non-trivial fraction of that deals with time. Now, Google's time code is no better or worse than anywhere else. We think it's pretty typical. And what we see is some of this code is very complicated. Some of it's obviously wrong. Some of it's subtly wrong. And every once in a while, some of it looks good. And some of the reasons for this are that time zones are complicated. Calendars are complicated. Daylight savings time is very complicated. It seems almost every 6 months there's some news article about some piece of technology that did the wrong thing during a daylight savings time transition. We can probably look forward to that again in about a month and a half. And programmers don't have a good workable mental model for how to think about and how to reason about time in their code. And time programming libraries historically have been lacking in some areas. So for the past couple years, my colleague Bradley White and I have been working to fix these problems within Google. And since we don't believe our problems are unique to Google, we think our solutions might be useful to others outside of Google as well. So before any meaningful communication can take place, we need to agree on the vocabulary we're going to be using. And then I'd like to move on and talk about some of the classic time programming APIs that we've all used and have shaped most of the time programming code that we see today. And then I want to give you a simple mental model that will help you reason about your code and think about time concepts. And then I'd like to leave you with a handful of pro tips that you can start using today in your existing code to help improve and simplify your time programming. So let's get started talking about the vocabulary. I'd like to talk about civil time, UTC, absolute time, and time zone. A civil time you can think of as just normal human time. It's when someone asks you what time it is, you look at your watch and you tell them it's 9:04, and that's a civil time. A civil time is fundamentally 6 individual fields that represent the year, month, day, hour, minute, and second. We typically use the Gregorian calendar, and in programs, civil times are typically represented by a type like a struct TM or a stood TM here. Or even a civil time could be 6 separate integers representing year, month, day, hour, minute, second. Even a string, like right here, this string is still a civil time. It's year, month, day, hour, minute, second. That brings us to UTC. UTC is the predominant international time standard used throughout the world. UTC is basically the time, the clock that we all synchronize our watches to, and we use this to agree on what time it is. It's the basis for all the local times around the world. In UTC, there is no daylight savings time. There are no transitions. Every day has exactly 24 hours. And the UTC clock ticks SI seconds. So a second in UTC, every second is exactly a fixed length defined by an atomic clock. And UTC uses leap seconds so that the UTC clock kind of stays in sync with the solar clock, where the sun actually is. And then I'd like to talk about absolute time. And absolute time uniquely and universally represents a specific instant in time. This instant is something that everybody would agree on when a particular instant is. The fact that this talk is happening right now, it doesn't matter where you are, where you may be watching this. Absolute times are time zone independent. Absolute times are typically represented as a count of some unit since some epoch. And classic examples that we're all familiar with are time t is a great example of an absolute time. In C++, stood chronos system clock time point is another good example. Or really, you could have any integer counting something since some when would be a fine example of an absolute time. And just to show the relationship between absolute and civil time, if you think about when Neil Armstrong first took the very first step onto the moon, that first step happened at some specific instant in time. Everybody would agree on when that happened. But where you or your parents were, sitting in your living room and looking at the calendar on your wall and the clock on your wall, that's the civil time for you when you saw that happen. The civil times for where you were may be different for people all around the world, but he didn't take his first step again an hour later for the people one time zone over. That happened exactly once. And then this brings us to time zones. Time zones are how we relate absolute times and civil times. Time zones give us the rules for converting between absolute and civil times. These rules are defined as offsets from UTC. These rules can change over time. So the notion of a time zone includes a whole history of potentially different time zone rules for different periods of time. These time zone rules are established by local governments, so sometimes they can be quite complicated. And many time zones use daylight savings time rules, so they change their offset throughout the year. And these strings in green down here are examples of valid, good time zone identifiers. They're typically represented like a continent and a major city in a certain area. So America, New York. The time zone we're currently in right now is called America, Los Angeles. Australia, Sydney is another one. PST, we typically think of as Pacific Standard Time. That's not a time zone identifier. It's not a valid time zone identifier. Now, some interesting time transitions. So we'd like to think that time transitions happen like daylight savings time is like an hour, spring forward, fall back. That's really not how, it's not how it always works. For instance, in the United States, even the Arizona Phoenix time zone doesn't use daylight savings time. Asia Kathmandu jumped 15 minutes in 1986, and that was not because of daylight savings time. So you can have time transitions that are not because of daylight savings time. In Australia, Lord Howe uses a 30-minute daylight savings time offset. So even if you think that daylight savings time is in effect, it's not always 60 minutes. And Pacific Apia, in 2011, they skipped the whole day of December 30th. It just doesn't exist there. And in that particular case, they were switching sides of the international date line. And Africa, Cairo, used to skip the midnight hour during their springtime daylight savings time transition. Actually, as of this year, they no longer do that. They no longer observe daylight savings time. But previously, before this year, there was no midnight on this day. There was no 0 hours, 0 minutes, 0 seconds on this during this transition. And African Monrovia used to use an offset of 44 minutes and 30 seconds. So transitions aren't always a nice round number. So the takeaway I'd like you to remember here is don't try to special case time zone transitions. Don't try to write code to say, okay, I know there's a transition, let me figure out what I'm supposed to do. There's over 500 time zones. There's updates to time zone data maybe about 8 times a year. So it's way too complicated to try to write that special case code yourself. And now that we have a vocabulary, let's look at a very common way we represent times in computer programs as a string. And let's just kind of figure out what's in the string. Let's diagram it. So these first 3 fields here give us a date, and here's a time. And together we know that's a civil time. It's 6 fields, year, month, day, hour, minute, second. And this green number here is a minus 7 hours here. This represents an offset from UTC. So this kind of takes the place of like a time zone. And this whole thing together, a civil time with this offset, gives me an absolute time. So this whole string here represents a specific instant in time. It doesn't matter what time zone you're in, this string represents a specific instant in time. So now I'd like to talk about some of the classic time programming APIs. Not a whole lot here. Hopefully most of this will be review for people, but these are the classic time APIs. They're still with us today. These APIs have shaped most of the modern time and time zone libraries that exist today and lots of the time code that exists today. And fundamentally, they're based around this type called time t. And a time t is a count of non-leap seconds since January 1st, 1970, 0 hours, 0 minutes, 0 seconds in UTC. So a time t value of 0 represents this date and time right up here. That date and time we typically refer to as the Unix epoch. So you may hear me say that. And a stood TM or a struct TM. This represents a broken down year, month, day, hour, minute, second. There's a handful of other fields in there as well. But fundamentally, a time t is an absolute time, and a struct TM is a civil time. And we're also given 2 time zones with which we can work. We can work in the UTC time zone or the local time zone. And the functions we have are to go from a time t to a TM. We have this GM time function. And if we want to do that in the local time zone, we have a local time function that will map from a time t to a TM. If we want to go the other direction, in the local time zone, we can call mctime to go from a TM to a time t. And in UTC, there's really no corresponding function for us, but that's because in UTC, since there's no offset transitions, you can actually just do arithmetic with the fields of the TM in order to get the absolute time. So I just want to look at a quick example of using these classic APIs. There's nothing new or fancy here, so there shouldn't be anything too surprising. I'm assuming some format function that just takes some format string and a struct TM. You can imagine this is implemented with stirf time or put time. But this example here, let's just look. Again, we're going to be creating a time t called now that represents the current time, the current absolute time. In this first block here, I'm going to use this gmtime_r function that takes the current time and fills in the struct tm with the year, month, day fields, the civil time fields that correspond to this current time. And I'm just going to format it. This %f is shorthand for year, month, day separated by hyphens, and %t here is shorthand for hour, minute, second separated by colons. And down here, this last block here, we just do the same thing, but we use the local time function. And we'll just break down the current time in the local time zone, and we'll fill in the struct tm, and we'll just go ahead and print that as well. And now, this is all fine. It works perfectly well. The problem is the fact that there's only support for 2 time zones, yet many time zones exist. And the fact that many time zones exist has led to many potentially complicated workarounds to support all these different time zones. And most of these workarounds boil down to a technique that we call epoch shifting. And we're going to go ahead and look at that now. So let's see how we can add support for arbitrary time zones. Most examples of epoch shifting boil down to a function that looks like this one right here. I'm calling it getOffset. They're typically named something like getOffset. It takes a time, an absolute time, and some indicator of a time zone. In this case, we're passing a string to indicate the time zone name. And it says, in this time zone, at this time, what's the offset? So that's the fundamental getOffset function. Now let's see what we're doing. Again, we get the current time. Now this first block here, I want to say, I call getOffset in America, New York, at now, at the current time. Give me the current offset. Then I'm going to take that offset and I'm going to add it to now. And I'm going to store it in another variable here I'm calling now NYC. And then I call this GM time function. These 3 lines here are just like they were on the previous slide. I break down now NYC, and I fill in the struct TM. And I'm going to go ahead and format the time, the year, month, day, hour, minute, second in New York City. Now I want to go back the other direction. So given my now NYC, my local time t, I say getOffset for this time, now NYC, again in America, New York. And since previously I added the offset, here I'm going to go ahead and subtract the offset because I'm trying to undo this operation. And I get now UTC. And so the question here is, are these 2 guaranteed to be equal? That's one of my questions. But let's go ahead and take a look at some of the other problems that we see with this code. I'm going to say the most fundamental problem here is that now NYC is not really a time t. Let me explain. There's 2 ways I can think about what I'm doing here. I'm taking now and I'm adding an offset to it. So either now NYC doesn't represent now, it represents some other time that's offset seconds or whatever away from now, so it doesn't represent now. Or I could say, well, I'm going to pretend it actually does represent now, and I've just shifted the epoch instead of the actual instant in time. And so if we look at how this code is being used, it's named now NYC. Clearly the intent of this code is that this point represents now, just in some other time zone. So what's happened here is I've shifted the epoch, but a time t is defined to have an epoch from a specific epoch. So if I shift that epoch, it's not really a time t. This should be a different type. I should call this a my time t or an NYC time t, for example, perhaps is what I should call that. But I don't. I call it a time t because this function I'm calling right here, gm time, expects a time t. So I put it in a time t anyway. And then what's another problem? What is this offset? So as the person writing this code, I have to be somewhat of a time expert because I have to understand, what is this offset? Is this an offset from UTC to me or from me to UTC? And I need to know that because I need to figure out whether I add or subtract here. We've seen lots of code that, it looks right, except this sign is wrong. So it's not immediately clear whether you're supposed to add or subtract this thing. Additionally, when I break down this now NYC using this function gmTimeR, some of the fields in the struct tm aren't correct. For example, is DST will always be false since UTC doesn't have any daylight savings time. And another big problem is this block down here doesn't actually work. So what we're doing here is we're calling getOffset, and we're passing in now NYC. We previously just said up top here that now NYC isn't really a time t. We're calling it a time t, but it's not really a time t. But getOffset expects a time t, so if I pass something that's not really a time t, getOffset may not return the right value. And in fact, for times that are near discontinuity, some type of offset transition, it actually will give you the wrong answer. And so I'll say that the answer to my question before was, is this guaranteed to always be equal? And the answer is no, it's not. It will sometimes, and maybe when you're writing the code and you're testing the code, it's the same. But then when you deploy and run the code, whoops, it's wrong sometimes. So the takeaway here is, I want you to remember that there's really no such thing as a local time t. There's a time t that's a valid actual time t, and there's really not a local time t. So now I'd like to give you a simplified mental model that will help you think about time concepts and reason about your code. And I hope that when you see this model that I'm going to show you here, you look at it and say, oh, that's it? Well, duh, that's so obvious. And hopefully it's unsurprising that it only has the same vocabulary that we've already been talking about. And what this is here is this is just showing the relationship between these things and formalizing the relationship between these concepts. There's the concept of an absolute time, which we've already been talking about. There's the concept of a civil time, which we've been talking about. And the time zone is all the rules to relate these things. You can imagine for some function f of an absolute time and a time zone, you can compute a civil time. And for some other function f of a civil time and a time zone, you can compute an absolute time. The domain of all the absolute times are time zone independent. Same with civil times. The whole domain of all the civil times are themselves time zone independent. Time zones are only important when you want to map between the two. And so this model actually applies to any programming language and any date time library you may be using. And now, since I said this is simple, I should probably point out what's missing. It's probably simple because it's missing a few things. So what it's missing are the fact that these time zones are opaque. You can't take these time zones and say, give me the offset at some point in time, because we don't want you to do any epoch shifting. You shouldn't have to take that offset and add it to anything or do any arithmetic to it. That's what a time zone library is supposed to do for you. So there's no access to offsets, no local seconds. There's no access to the future and past transitions. And when I think about these missing features, this is Ken Thompson, one of the principal inventors of Unix. He was once asked about the Unix file API, and the question was about, well, where's this feature, and how do you do this, and where's all this, record support, and how come it's missing all these things? And his response was, these concepts fill a much-needed gap. And so let's take a look and see how these classic APIs fit into this model. So I've written some of the types and functions here in green. I think these are a pretty good fit. A time t is a fine absolute time, other than it only has second granularity, but that might be fine in some cases. Stood chrono system clock time point. It's another, that's great, fits very well. The things I wrote in red here, I'll say they fit, but they could be improved. So for time zones, there's only support for UTC and local time, so we could probably improve that. And for civil time, there's the struct TM, which works for a civil time. It leaves a little bit to be desired. The years are offsets from 1900. The months are zero index, so it's not the easiest thing to work with. And for going from absolute to civil, we have this local time function, and civil to absolute, we have make time. And again, those work just in the the local time zone. And so to try to fix these problems within Google, we built a new time zone library that very closely matches this model. We call it CCTZ for the C++ time zone library. And in blue here, here's some of the types and how this library maps it into this model. For absolute times, we have the CCTZ time point. Now this is pretty much just a system clock time point. It's defined only for the system clock. It just has a wider range, has 128 bits of range to avoid the 292-year issue, because within Google we wanted actually one time type. But it implicitly converts from a system clock time point. Time zone is represented by the CCTZ time zone class. All these things are in this namespace. So time zone can represent any time zone. A civil time is represented by a CCTZ breakdown. You can think of it just kind of like, I want to say, a better struct TM. It has the civil time components, year, month, day, hour, minute, second, and a few other fields that we'll see in a moment. And to go from an absolute time to a civil time, there's the break time function. And to go the other direction from civil to absolute, there's the make time function. And we're going to take a look and see how these things work in some examples, and let's start off with a hello CCTZ example. Yes?
I have a question. So whenever you said the civil time, you're assuming daylight savings is on.
I'm not assuming daylight savings time is on.
Meaning it's going to honor when the conversion happens from UTC and back?
So the question is about conversions with daylight savings time, and I have a slide, in about 2 slides, we will definitely cover that. So just hold tight, please. So hello CCTZ. So this I just want to show to give you kind of a feel for the API. We did this in Google's programming style conventions. You may or may not like that. Please don't crucify me, but that's how it's done here. So most of this code is going to start off looking the same. We want a time zone. I'm going to declare a time zone for Sydney, Australia. I declare this variable. I call the function load time zone. I tell it Australia, Sydney. I pass in a pointer to the time zone object. Load time zone will return bool if it, indicating success or failure. It will load the file. It will load the time zone from the time zone data on disk. Usually on Linux, that's like user share zone info. It'll also then cache it, so subsequent calls to this are very fast. Then here, we're going to call make time. And to make time, I'm going to pass 6 fields. And we probably know what these 6 fields are. They're a civil time. So I'm going to say 1969, July 21st, 12:56 in the afternoon, 0 seconds, in Sydney, Australia. And we know that from our model, when we think back to the mental model, a civil time and a time zone gives me an absolute time. And that's what make time is doing right here. So this gives me the absolute time for when Neil Armstrong first walked on the moon. That's the absolute time when that happened. And then I'm just going to come down here and I'm going to call CCTZ format. Again, this is very similar to stirref time, except there's a few extended format specifiers that I won't be talking about but are documented. And format takes an absolute time and a time zone. And it's going to go ahead and format this. A time point, yes, which is an absolute time. Yes, it takes a time point and a time zone. And down here, I'm going to go ahead and load up another time zone. I'm going to load up the time zone for America, New York. Now, I'm not checking the return value here for 2 reasons. One is because checking the return value on the slides kind of takes a bunch of space. And also, the definition of load time zone is defined that if it fails to load the time zone, it sets the argument here to UTC, which a lot of people have said is the default behavior they want. So That's why that's not being done here. And here we're going to call make time again. And I'm going to pass in a different civil time. So here I'm passing July 20th at 10:56 in the evening in New York, and that gives me another absolute time. But these two time points are guaranteed to be identical. These are the, this civil time in New York and this civil time in Sydney correspond to the exact same absolute time. Now let me mention a couple things briefly about the implementation of the CCTZ library. One is it mostly follows POSIX conventions in that it ignores leap seconds and it uses the proleptic Gregorian calendar, which is the standard calendar we all use today. It just extends it forward and backward in time. It uses the IANA time zone data from the local system, for example, in user share zone info. And fields, when you call make time and you pass in a year, month, day, hour, minute, second field, any fields that are out of range will automatically be normalized to be in range. So if you pass in October 32nd, for example, it will normalize that to be November 1st. And we'll see in an example coming up here about how that can be very useful. It's faster than the libc equivalents. Now, we have run a bunch of benchmarks. It's hard to tell, it's hard to say for certain that every machine, every compiler, every hardware thing, it's faster. So I'm going to say in every benchmark we have, it's faster. I don't think speed is the reason to use this or something like this, but it shouldn't be a reason not to use it. And the implementation gives us some very nice default handling of discontinuities, for example, daylight savings time. So we're going to go ahead and talk about that now. We're going to talk about the daylight savings time transitions and how that works. Because these are the real complicated things that end up in pages and pages of comments followed by like one line of code. So first of all, daylight savings time is in quotes here because what we're talking about here are skipped and repeated civil times, and whether that is because of daylight savings time or not is immaterial. So we always think of these as because of daylight savings time, but they're not always because of daylight savings time. And let's just start off here looking just at this graph here on the left. This vertical axis here is absolute time. This horizontal axis here is the civil times, like 1 a.m., 2 a.m., 3 a.m., 4 a.m., etc. In the case of spring, in this example, let's say it's America, Los Angeles. In the case of the springtime, we skip the 2 o'clock hour. So we go from like 1:59 and we jump over to 3 a.m. This diagonal, the blue line here is time. It increases at 1 second per second. So the question is, what happens if you ask for, give me the absolute time that corresponds to 2:30 a.m. on this day? So the question is, what happens then? Well, what we could do there is, first of all, we could just give an error. We could say, oh, there is no 2:30, and you're done. You can't do that. Pardon? You could throw an exception. You could return some type of error. But we'd like to try to do better than that. So what could we do? Well, we could say that 2:30, if this line here were extended down, it would intersect about here. So we could give you this absolute time that kind of corresponds to this first intersection. Or we could maybe say, well, if this line extended up here, it would intersect here, and we could give you this absolute time. Or we could also say, well, the time discontinuity happened right here, so we could just give you that time right there. And so the default behavior that we picked for CCTZ is that it follows the as-if rule. It says, that is, what time would we give you if there was no discontinuity? If there was no discontinuity, this line would just be extended up, and we would give you this point right here that corresponds over there. And in fact, that's what we do. It ends up that we end up using the pre-transition offset is the way that works. And we think that really matches with people's just intuition. If you think about waking up, after there was a daylight savings time change that evening, and in the afternoon someone asks you, what time is it? And you look at your watch, you say, oh, it's 5 p.m. Well, it's really 4 p.m. We tend to do that for about a day. Yes?
So, when this happens, someone asks for time in between. Is that usually a programming error or like a user input error or something else?
The question is, if that happens where someone asks for a time that doesn't exist, is it usually a programming error or a user input error? It could be those. It could just be that you're trying to write a code to bucket log data into hours and present it on the screen, and you just happen to be presenting data on a day where there's 23 hours in that day. So you might be iterating the hours in that day. So there's very legitimate cases where you might want to ask for, say, 2 a.m. on this day. That's not always because of an error. So it depends on the case. Now let me say the fall case is very similar. In this case, the 1 o'clock hour is repeated. So there's 2 points in time that have the label of 1:30 a.m. in the fall. And so again, when you ask for 1:30, which one do we give you? Do we give you this one or do we give you this one? And again, we just follow the as-if rule. If there was no transition, what time would you get? Well, you would get this one right here, and that's what we give you. Now we think this is a very good default behavior. It's what our make-time function returns. Yes? Yeah, yes.
So if we were to get the absolute time for like, let's say 2:59,
Mm-hmm.
and then the other time at 3, I would take the difference, right? So they get something that's unexpected. The difference between absolute time, right?
Well, if you're talking about difference between if you're doing difference between absolute times, you're in that question. You're a little bit mixing. The question is, if I take the difference between 2:59 and 3 a.m., couldn't I get something that's maybe negative or funny? And I'd say in that case, you'd probably want to rethink a little bit about what you're doing because you're mixing the notions of civil times and absolute times. You're thinking of civil times, but taking a difference in absolute times. So I think if you clear that up a little bit, I think you're going to find that you don't actually want to do the computation exactly as you described. So like I said, this is the default behavior we give. And we think this is good in most cases. However, we do understand that there may be cases where you need to have some special handling for when some time doesn't exist or when it's repeated. And so we have another function and that I'm showing here. We have 2 versions of make time. We have make time down here on the bottom. This is the one I was just describing. This is the one that does the as-if behavior. It uses the pre-transition offset. And I think that's typically the one you would want to use. The arguments to make time are 6 fields, a civil time, and a time zone. So you pass year, month, day, hour, minute, second, and it's going to give you a time point. There's no error case here. In the case of repeated or skipped transitions, it's going to pick something sensible. Now, if that doesn't work for you, there's this other version called make time info. It takes the exact same arguments, year, month, day, hour, minute, second, and a time zone, and it returns this time info struct. And the time info struct tells you everything you need to know about that conversion. It tells you whether that civil time you asked for was unique and existed, or whether it was skipped and didn't exist, or whether it was repeated. Those are the 3 possibilities. It also tells you, if we think back to the graph, those intersection points, it tells you what would the time point have been if we used the pre-transition offset? What was the transition point itself? And what was the time if we had used the post-transition offset? And from these 3 fields here, these 3 values, you should be able to compute any reasonable time point you could possibly want, including just give an error. Yes?
Explain the use of it. Why would you use N64s for year around 1 billion times the size of the
Because we needed... The question is why use int64 for years? And the reason is because internal to Google, we ended up wanting 1 time point that could represent all of the times for all the applications. And we ended up using basically a 128-bit representation of nanoseconds. And that ended up being able to produce more than 32 bits of years. So it's not a full 64 bits of years. It can't handle that much. And also it gives you this Boolean indicating whether or not it normalized any of these fields. Because again, by default, it always normalizes the fields. If you ask for October 32nd, it will give you November 1st. But if you want to treat that as an error, you can, that it will tell you if it had to do that. So mostly I would say, generally make time that just returns the time point is probably what you want. And going the other direction, break time. This is going from an absolute time, a time point, to the broken down civil time. So we call it break time. You give it a time point and a time zone, and it returns this breakdown structure. Again, breakdown is a lot like a struct TM. It has the year, month, day, hour, minute, second. Those are the main civil time components. There's additionally a handful of other fields in here that you might need, like weekday and subsecond and year day. There's also these three down here, this offset, is DST, and aber, like the time zone abbreviation. I think you should probably not be using those last three fields. You should probably ignore them. The reason they exist is for backward compatibility with some old APIs that might need to use these things. But if you're using a time zone library properly, you don't care what the offset is. You don't care whether it's daylight savings time or not, because your code is generic and it works for all time zones at any time point. And so you don't care about these. So I would say try not to use them, pretty much ignore them if possible. Now I'd like to look at some examples of real programming examples that are common and what they look like using the CCTZ library. So again, in this case, translating civil time. So translating a civil time from one time zone to an equivalent civil time in another time zone. All of our examples are going to start off pretty much the same. We're going to declare a time zone. We're going to load up that time zone. So here's all the data for America, Los Angeles. Now this time zone object is actually really, really small. It's about 1 word, and you can pass it around by value. All the types in here are little value types. So we're going to just load this up. Then we're going to call make time. We're going to get the absolute time for when this talk started. We're going to say make time 2015, September 22nd at 9 a.m. That's when this talk started in this time zone. Down here, I'm going to go ahead and load up the time zone for America, New York. And then I'm just going to go ahead and use CCTZ format, and I'm going to format this same time, the exact same absolute time in 2 different time zones. So the only thing that's changing there is the time zone. This %z here gives me a numeric offset for the time zone at that instant. And this big Z here gives me like the string abbreviation. I'm including these here just so it's kind of easy to see, read in the output. And so the output of this program, the output of this program is talk starts at 9 a.m. and a -7, that's PDT, Pacific Daylight Time, which is where we are right now. And the talk starts at 12 noon in Eastern Daylight Time. So it's very easy to translate a civil time from one time zone to another. And the things to note here are there's no mention of offset. I mean, other than the fact that I'm printing it just so we can read here. But there's no, I don't use an offset. I don't compute with an offset. All I'm doing here is just calling a couple of functions and perhaps converting types. So we just saw what formatting looks like. Let's see the other side. What does parsing look like? So the string I'm going to parse here, I've defined up here. It's a civil time. I name it civil string. It's 2015 9/22 at 9:35 a.m. So that's the string I want to parse. And then we're going to go ahead and load up the America Los Angeles time zone. This time I'm going to call CCTZ parse. And that takes a format string, the same type of just like a stir-p time format string, so you're probably pretty familiar with this. I'm going to parse out a year, month, day, hour, minute, second from this data here, from this time string. I'm going to say parse that with respect to the LA time zone. And then this is going to give me the absolute time that I parsed out of there. And it returns bool indicating whether it was able to parse or not. And then down here, I'm just, this isn't really about parsing, but I'm just going to call stood chronos system clock now to get the current time. And I'm going to see if now is after this time I parsed, then this talk is running long. Otherwise, it's on time. And when I ran this many days ago, I was definitely on time. I don't know where I am now. Okay, so I'm running long. Thank you. All right, So now let's look at an interesting example of adding months. So this is fundamentally a civil time computation. You can't add months in the absolute time domain. There's no, stood chrono months duration. That doesn't really even make sense. It's not the right question to ask. So if you want to think about adding months, you really need to be doing that in the civil time domain. And I'm going to show how you can do that with CCTZ. Again, we're going to start off, unsurprisingly, load up a time zone. Get the LAX time zone since that's where we are today. I'm going to get stood chrono system clock now to get the current time. And I'm going to call break time. I'm going to break down the current instant in the LA time zone. And I'm going to get this breakdown structure. Remember, breakdown is a civil time. It has year, month, day, hour, minute, second. And then down here, I'm going to call make time again. So I want to go from some civil time to an absolute time. And I'm going to say, from this breakdown, give me breakdown year, the current month, plus 6. And I want the first of the month. I want 6 months from now, the first day of the month, I'm just picking. And 0 hours, 0 minutes, 0 seconds in LA. Then I'll go ahead and format this. So I'm initializing the absolute time then. And I'm going to go ahead and format both of these. Now, when I ran this the other day, was 9:17 at 9:02 a.m. And the output for 6 months from now is, well, September, October, November, December, January, February, March. So month 3, and that's what we get here, March 1st. And so the thing to note here is that this arithmetic right here is done in the civil time domain. I'm adding 6 civil months. And the fact that this may become larger than 12 and need to be normalized is fine, because make time always normalizes. It will take that month and it will normalize it, roll over into the years field, or roll under as necessary. And it does this computation completely in the civil time domain. Yes? Yes. Yes, it picked up the fact that we went from daylight time to standard time, and printing. Yes.
So, can there be two results typically, for that kind of computation, like if you're going through a change or a
Yeah. So the question is, can there be 2 results? And yes, this is, if you remember the graphs for spring and, fall daylight savings time transitions, when you're going from a civil time to an absolute time, there can be cases where times are repeated or skipped. And that's what I was saying about make time picks one, we think a sensible one, but there's a different version. If you want to know that there are 2 possibilities or multiple possibilities, you would call the make time info function, which would give you all those details if you care about them. In many cases, if you're computing, 6 months from now, you probably don't care about that. Yes, Jeff? Oh, okay.
What happens if it's July 31st and you want to go 6 months and keep the day?
Okay. So the question is, what happens if it's July 31st and you want to add 6 months and you want to keep the day? What would happen is if you end up, saying, all right, thank you. The question is, fundamentally, we always think about this as, it's January 31st and you add 1 month and you want to keep the same day. Well, February 31st doesn't exist, so what would happen? It would end up normalizing that day as well. So you would end up getting like March 3rd or something. So it would normalize the day as well. It doesn't cap the day to the end of the remaining month. If you want that behavior, you'd have to implement that, but all the fields just get normalized. Okay, so for one more example here, this is a very common one. This is the case where you want to floor to midnight. This code exists all over the place. And I have midnight in quotes here because I think midnight is a bit of a bad term. It's somewhat of an ambiguous term. When you just colloquially speaking, when you say midnight, you tend to mean tomorrow's midnight. You don't mean really today's midnight. If you say, I'm going to be home Friday at midnight, you actually mean Saturday morning at midnight is typically what people mean. Additionally, midnight, you think about 0, hour 0, minute 0, second 0 when you say midnight. You think of those zeros. And as we saw with Africa Cairo, that doesn't always exist. Sometimes midnight doesn't exist. So instead, I would encourage you to use terms like, in this case, I'm saying floor today. We could say that every day has a first moment, a first instant. That instant might not be midnight. So we'll call it floor day, day start, start of day, any of those things would be fine. So in this case, we have a function floor day, and I'm gonna actually skip down here to main and just look at using this real quick, and then we'll talk about how we implemented it. So again, we simply load up the America Los Angeles time zone. I'm gonna get the current time, stood Chronos system clock now. I'm gonna call floor day, so I'm gonna floor now in the LA time zone, and I'm gonna get another absolute time. I called it day, and I'm just gonna go ahead and format both of those in the LA time zone, now and day. And when I ran this the other day, it was 9:12 a.m., and the beginning of the day is unsurprisingly 000. So let's see how we implemented floor day. So the arguments are, it's given a time point and a time zone, and it's supposed to return the time zone, the time point for the first instant of that day. So we start off, we just say breakdown or break time, and we get a breakdown, so we get all the civil time components of that time. And then fundamentally what I want to do is I want to just take that civil time and I want to ask for the midnight hour and have it turn that midnight hour into a real absolute time, a real time point. Now, since the definition of this function is that it must give the first instant of the day, the default behavior, the as-if rule that make time would give us is not really what we want. Because the one special case there is if you think about the graph, the springtime graph, where a time might be skipped, the first instant of that day is the transition point if the time was skipped. The transition point would be the first instant. So what we're doing here is we're just using time info. So we would say make time info of this time's year, month, and day, hour 0, minute 0, second 0, and I get the time info, and I say if that time was skipped, then return the transition point, because that would be the first instant of the day. Otherwise, return pre. Pre would always be the first instant then. And so this function will work for any time zone, anywhere in the world, given any funny daylight savings or other transitions, forward, back, skips, repeats, anything like that. This should work anywhere. Yes?
The transition point is the filled in
Yes,
circle?
yes. The question was, the transition point was the filled in circle on those previous graphs, and the answer is yes. Okay. Now, again, we built this library to fix real problems at Google. And so we end up doing a lot of refactoring of old code. So I want to just look at one quick example of a refactoring of old code, of real refactoring that we did. And what I like to do when looking at these APIs is old APIs and refactoring them is just look at this function signature and then think about this mental model and think, does it even make sense what they're asking, what they're claiming they're going to do? A lot of times it doesn't. In this case, where this function get local time, and it's given a time t and a time zone. So an absolute time and a time zone. So I know from the mental model, given those two things, I can compute a civil time, the corresponding civil time. And the output I want here is hour, minute, and second. So, okay, phew, this one passes the sanity test. It's possible. So let's see how they did it. Well, just with a couple seconds of looking here, it's going to jump out that, again, this is the epoch shifting solution. This is very common. Instead of, in my example earlier, I called it get offset. Here they called it calc offset. But it's the same thing. Calculate offset in this zone at this time and give me the offset. Then I take that offset, I add it to the time, and I get what's called adjusted time. And then I break it down with GM time, just like we saw in the earlier example. And then I just assign the hour, minute, and second fields. So nothing too complicated here, or nothing too surprising here. But let's see how we can improve this. Let's say we want to refactor this, but maybe there's a whole bunch of callers to this function. We don't want to change the signature. We just want to change the implementation to improve the code. So using CCTZ, here's what the code would look like. Since I'm given a time zone string, I would just declare a time zone and load up the time zone that I was given, that was passed here. Then I'll take this time t I was given, and I'll use stood Chronos system clock from time t, and I'll make a time point that corresponds to that argument. Then the real work comes by just calling this one function break time. I break down that absolute time in the time zone, and I get a breakdown. Then I just assign the hour, minute, second here. So the thing I want you to notice about the difference between this implementation and this new implementation is that there's no mention of offsets, there's no logic, there's no arithmetic. I'm not adding something. I don't have to think, am I supposed to add that offset or subtract that offset? I'm pretty much just converting types. So this is pretty close to if it compiles, it works. Now let's say there's actually not too many callers to this function, so updating the function signature is, maybe that's okay. Let's see what we could do if we could maybe improve this a little bit more. What I might do is I might say, well, instead of passing a time t, I'll just pass in the time point. It could be a CCTZ time point, or even a stood chrono system clock time point would be just as good. And instead of passing in the time zone as a string, I'll have the caller just pass the time zone as the CCTZ time zone object. The benefit here is now the caller can load up any time zone they want. They can also handling the errors of loading the time zone if they want. Previously, both versions of the code just ignored any load failures on the time zone. So this is an improvement. And then the body of this function basically boils down to one call to CCTZ break time, and then we just assign the output. So really, there's really no need to have this function at all. The real refactoring here is just to delete the whole thing and just have the caller call CCTZ break time. And we see that happens a lot with a lot of time utility code. Now that we have CCTZ, a lot of it, hundreds and hundreds of lines of code are just kind of saying, oh, this is redundant, it's not needed anymore. Yes?
Did you ever have to identify the time point with the time zone it was created with?
Do you ever have to identify the time point with the time zone it was with the time zone it was created with the time zone that the time point was created with? You can. I could say there's no need to. It depends on what you're trying to do, whether or not that's necessary.
Yeah, my question was mostly could the time zone could it have been a member of the time point class?
The question was, could the time zone have been a member of the time point class? What you mentioned is actually very similar to how they do it in Go. So there is some precedent for what you're saying there. But we didn't do that primarily because we want to reuse the stood chrono time point concept, which doesn't really have that baked in. Additionally, the notion of an absolute time is really time zone independent. It's a time zone independent concept. So some final thoughts I'd like to leave you with here are, one, remember this mental model. It's real simple. Absolute time, civil time, time zone. The relationship absolute time plus a civil time gives you absolute time and a time zone give you a civil time, and civil time and a time zone give you an absolute time. When you're talking about these concepts and coding with these concepts and adding comments, use a clear vocabulary. Try to use these terms, civil time, absolute time. Just saying time is kind of ambiguous. It's not really clear what you mean. In your format strings, prefer to use this %z. That's the thing that puts the numeric offset in your format string. And what that does, that ends up letting your format string represent an absolute instant in time. That moment is unambiguous and anybody could parse it. Never compute with UTC offsets. There's no need for you to do that. It's never necessary. Don't do arithmetic with time t's unless you're implementing a time zone library. I would say that's probably the only exception. For this breakdown, CCTZ breakdown, compute it when you need it. Don't really pass it around. Represent points in time as time points, as absolute time points. And if you need to pass in this notion of a time in some time zone, pass in a time in a time zone, and this thing can be computed as necessary. And do calendar-like calculations in the civil time domain. Don't try to do things like adding months with stood chrono time points directly. Do those calculations in the civil time domain. And a brief note on terminology. Use the term UTC instead of GMT. When you mean UTC, say UTC. UTC superseded GMT in the early 60s. We can start saying UTC now. And this CCTZ library is available today on GitHub. Feel free to take a look at it. Right now, it works on Linux and almost works on Mac, other than if anyone works at Apple, come talk to me. We have a couple of questions. But so it is available today. You can take a look at it. And Any questions? Yes. How does this stuff relate to the Olson database? It uses all the time zone data from the Olson database. That IANA time zone data is all from the Olson database, and that's the data this works with. Yes. Yes, right.
Excuse me for the unfamiliarity, but are your time zones revision? Like if I were to compute the 6 months difference for Central Time Zone in 2030, and then like time zones change.
Yeah.
Yeah,
so absolutely, time zones do change. Like I said, there's roughly 8 to 10. The question is, do time zones change? If you compute 6 months difference in 2030, might that change? And the answer is absolutely yes, that might change. I would say, be careful if you're computing things that depend on time zones that far in the future. And in general, for something that far in the future, I would say if you're storing data, store your first order, your primary data. If the thing you need is to add 6 months to some time in 2030, store the absolute time that you know for sure in 2030, and store this concept of I need to add 6 months, and then compute that as you need it when it's close to 2030. Okay, sorry. This is Bradley White, my colleague here. He said, it won't change during the execution of your program. So that is true. That is true. Yes?
I noticed you used three functions.
Mm-hmm.
Adding. Did you consider operator overloading?
Free functions for adding what?
The offset and the absolute time. You had this beautiful equation, like civilian time equals absolute time.
Oh, yes. That was just actually an abstract, mathematical representation. That wasn't the code. The question was, when we add offsets, did we consider, instead of using free functions, operator overloading? I would say, in the CCTZ, we don't really add offsets anywhere. I think the adding of offsets was all in the old code that we.
I think making absolute time plus time zone.
Yeah, you had two different.
I see. The question was, could we have made absolute, like a time point plus a time zone, give you a breakdown instead of break time? And I think we probably could have. It would have been a little bit harder because in the make time direction, we want two versions, make time and make time info. So we just thought it was clearer to have function names instead of operators. Thank you. Yes? Yeah.
Maybe that was answered, but how the library behaves when you do an update, you have a long-running demo, and you perform the update to your time zone data.
Mm-hmm.
Will it pick it up?
Okay, so two questions. The first one was, am I aware of any work toward updating libc with something like this? And no, I'm not aware of any work like that happening.
We would hope that this might be the beginning of some proposals.
But sure, right. So I'm not aware of any existing work on that. And okay, I see session is over, but I'd be happy to answer that after. Thank you.